All right. Good evening, everybody. This is Eric Ranchart. I'm the president of USOMI, and I would like to welcome you on this webinar with George Shih, who will talk about... Hello?
Au début, j'ai failli envoyer tout balader.
This webinar will be about building AI superpowers for radiologists. And first, I would like to introduce George Shih to you. George is a radiologist. He's working at Weill Cornell Medical Center in New York City. And he also obtained a degree in electrical engineering. He obtained this degree in Paris at the École Nationale Supérieure des Télécommunications. George is the founder of a platform called MDAI, which is a platform that he used during his participation in the Kaggle competition, actually a challenge in developing algorithms. So today, I would like to welcome George for this webinar. I would also like to mention that you can ask questions by clicking the button on the bottom of your screen. It's Q&A, and there you can type questions. So we will answer the questions at the end of the presentation. And I would also like to mention that the webinar will be available for those who could not attend this live session, but we publish our webinars on YouTube, so you can find them by going to our website. So I wish you a good webinar. George, the stage is for you.
Thank you, Eric, and thank you for the kind introduction. Thank you to USOMI for the invitation, Nadia and Daniel and Paula for organizing. So today I'm going to convince you that AI is really a superpower that doctors and especially radiologists will have. That's going to make everyone Superman, Wonder Woman, or in the case of this slide, my daughter's favorite, which is Supergirl. So I'm going to also convince you that in addition to kind of having these AI superpowers, that in fact radiologists are the most important people in creating and building these new superpowers. So instead of being skeptical or afraid of AI, we doctors should be very excited about the future. And my guess is that in a few years, most radiologists will be able to create their own AI superpowers. And so with that, I'll get started. Let's see. I think Eric did an intro, and I don't have much to add except, I did study a couple years in Europe, mostly in Paris. I did spend a year in the south of France at a program called Eurocom, which had kind of other European students there, and it was a fantastic experience that I enjoyed. I'm currently in New York City. I've been in New York City since residency, and my background is computer science and electrical engineering. Let's see. So here are my disclosures. So Eric already mentioned I have a small internet startup, AI startup called MDAI. So why is everyone excited about AI? So there are many reasons, but I really like this quote from the CEO of IBM. And she says that AI has the potential to find solutions to the world's most unsolvable problems. And for me, that's inspiring because I think that definitely includes medicine. And in fact, I think we've seen a lot of countries also have great ambitions about AI. We've seen entire countries kind of develop healthcare AI strategies and plans. And this one, for the European audience is probably familiar, where the President Macron announced last year that he's launching big AI initiative, which really includes healthcare as a primary focus. He was interviewed by, there's a great interview by Wired magazine. If you guys haven't seen it, you should look for it. And the first thing he talked about in that interview was about healthcare. And here, there's a quote on there that says, healthcare AI is going to completely change the way they treat people, prevent diseases, and reduce the potential risk for patients. So I thought that was a really great example of how lots of countries are excited about this. I'm going to highlight China just because I was recently there, and they have also great ambitions to use AI in the healthcare space. So this is a trend that's not going to go away anytime soon because there's a shortage of doctors worldwide. And lots of, in particular in our field of radiology, lots of life-saving medical imaging is not able to be interpreted in a timely fashion because there aren't enough doctors or radiologists. And I'm going to put in a plug for a session that I'm going to moderate at the RSNA 2019 on the role of radiology AI in the developing world. So for those of you guys who are going to be at the RSNA, look out for that session. I want to start with a brief summary. I'm currently the chair of the scientific committee for informatics. And so essentially I get to see all the, abstracts from that category. And what we've seen is a huge growth of machine learning abstracts or AI abstracts, which is really not surprising. So 3 times growth compared with the previous year. And actually I didn't include it, but that it's roughly about the same from the previous year before that. So basically, machine learning has become the most popular category for, the informatics topic in RSNA. And I think this is very interesting because RSNA is probably the most international society that we have for radiology. And so it's a good indicator of what people are working on in the scientific community. And a lot of that, a few months or a year later ends up being, published in journals, but also, developed maybe further in research and eventually goes into the marketplace. So it's a nice way to try to predict the future, if you will. A lot of the growth comes from outside of RSNA. So if you look at kind of the traditional numbers of abstracts, and other categories are obviously not as popular now, but there's just looking at the numbers, there are definitely other kinds of people submitting abstracts to RSNA. So that's great. So we're getting people who never were really interested in radiology before, but because of AI, they're presenting at our conferences. The other trend I thought was very interesting, I'm obviously, this is the scientific category. We have lots of vendors who are submitting very high quality abstracts. And I don't think that's very surprising because a lot of the machine learning is being done by, at least formerly PhDs. They're still PhDs, but formerly academics, lots of PhD people who have machine learning experience. And so they're used to kind of, presenting at scientific conferences. Great, and obviously the vendor space, this is a pretty old slide, but is really, expanding pretty dramatically. I don't have any specific information about Europe. I'm sure it's also, very exciting to be in the AI space in terms of these healthcare startups. But I know I just recently went to China, and I went to one of the top kind of venture capital firms run by a guy named Kai-Fu Lee, who's pretty famous in China. He's pretty famous internationally, frankly. And his healthcare division told me that they had recently met 100 AI startups just in Beijing alone, working in more or less radiology AI. So lots of companies are trying to innovate in the space. And so probably the audience knows a lot about AI, but I like to kind of go through it. So what is AI exactly, and how do you think about it? And really, for me, the best way to think about it is that AI is really about prediction, right? And if you think about AI's prediction, then it makes it a lot easier. It is an advance in statistical methods, but it's not about kind of general intelligence, but it's about one aspect of intelligence, and that's prediction. So when you use an algorithm to look at a lung nodule, you're essentially predicting whether or not that nodule is cancer, right? And that's really kind of a lot of what we do as radiologists. And so my advice to radiologists is that we need to develop, AI insight. So we need to be able to see problems that we have as a prediction problem, right? And if you can frame your problem as a prediction problem, there's probably a good chance that you can use these newer AI techniques. Great. So what about deep learning? Because again, I like to go through the vocabulary because I think everyone talks about AI, but they really mean deep learning in most cases. So I'll kind of briefly go through it. So when you read about AI in a lot of the journals now, most people are really talking about the deep learning technique, which is a subset of the machine learning algorithms, right, using neural networks. And so for our purposes, whenever I talk about AI, I'm really referring to deep learning. And I think most people are as well, if you read the press. So what is deep learning? So the best way to understand it is to look at dogs versus cats, right? Because if you can understand this, I think you can understand most of the algorithms. So given lots of photos of dogs and cats, can you create an algorithm that can look at a new photo and tell you if it's a dog or a cat? So essentially what the machine learning algorithm tries to do, right, is to draw a boundary between, dog pictures and cat pictures, right? And in the older algorithms, the boundary was not always very good. And really the advance in deep learning is that we can draw these very kind of sophisticated boundaries between the different categories. And so that's, in my opinion, that's the real kind of innovation that presented in a graph form, right? And neural networks, so what is deep learning? So it's really kind of a series of simulated or artificial neurons that were inspired by the human brain, and they added some math formulas to it, right? And then when you put a bunch of these layers together, you get what's called deep neural networks. And so the term deep learning comes from, deep neural networks and machine learning, right? So that's what deep learning is. So what can you predict? So it turns out that deep learning is really good for basically all the kinds of data that we use in medical practice. So whether it's imaging data, text data, right? So all the kind of reports and notes, time series data like EKG, it's pretty good at it. So so what's the goal? So again, I'm going to go back to the superpowers, right? So the goal is that what we want to do is create, algorithms using data, right, and radiologist expertise, and create, superpowers that allow doctors to be more accurate, faster, right, and provide better patient care. And so that's really the ultimate goal for using AI. So what do you need for deep learning? So there are only a few slides that I think, that I would say are kind of the key slides. And this is one of them. So if you guys can remember this slide, I think it would be useful. So really, in order to build these superpowers, right, you need three things, right? So you need a GPU, which you can, it's a graphics card, a special graphics card that you can really go to the store and buy it or order it online. or ask your chairman to buy it, right? The second thing you need is a architecture loss function, and that's really just the algorithm. And there are lots of algorithms out there. Almost all of them are open source. You can download them and use them for free. And the third component is the labeled data. So in the case of radiology, we're usually talking about, the imaging data, X-rays, CTs, MRIs, et cetera, with annotations, because the deep learning algorithms require that we tell the computer algorithm where the abnormality is, right? So that it can learn. So those are the three main ingredients. So what's interesting, though, is that in terms of the algorithm, pretty much everyone is using the same algorithms, right? And these algorithms are evolving over time. They're getting kind of incrementally better. And maybe, there are kind of variations of certain algorithms for different specific tasks. But if you look at, if you had the opportunity to visit a research institution or multiple research institutions or other companies and kind of look at what they're doing, I think that most people would be using more or less the same algorithm. So really, if there's no differentiator in these algorithms, in my opinion. So the only thing that's really different is the data, right? And how it's annotated, right? And who controls the data and who annotates the data. So we do, right? Doctors do. And so this is really the key piece for building AI. So if you want to think about it in that way, the radiologists are really the ones who are building AI, right? Not the engineers. I mean, obviously the engineers play an important role. But really for you to build really sophisticated AI superpowers, it really depends on the radiologist. And for better or for worse, most of the imaging data that we have today, and there's a lot of it, is not annotated, right? And so it basically means you can't use it for machine learning, right? So this is good and bad, right? It basically means that anytime you hear about, a hospital or a company saying that they have access to, 5 billion images, it doesn't really matter, because unless it's annotated in a way that can be consumed by the algorithm, it's not really useful for that, for them, right? So I think there's still lots of opportunities, precisely because most of the data that we have access to is not annotated. And the only people that can really annotate that data are radiologists. All right, so why is this different from other kinds of applications? So I'm going to try to use an example from the self-driving car world. I think most of you guys are probably familiar with Tesla. Lots of other companies are working in the self-driving car space. So here on the left, we have a traditional application where you write program code line after line, and you do some if statements and for loops, right? And on the right side is your deep neural network, and that comes out of the box, right? You can download that. So there's a little bit of tweaking involved. There are hyperparameters and things that you can adjust, of course. But the main algorithm is this, right? And there's really, the way that you program the right side is that you feed it data, right? So let's look at a specific example, right? So how do you determine if a car is parked, right? So this is an important question for the self-driving car world, right? So if you're driving along, you want to figure out if a car is parked. Well, the old way is that you would, use a camera to kind of detect where the cars are and then track these cars with bounding boxes. And if the car hasn't moved, 20 pixels over the last few seconds and, et cetera, you have to kind of build these very complicated rules to determine if a car is parked. And it's very difficult to build a rule that encompasses all the scenarios, right? So with the new AI method, the deep learning method, the car is parked if the neural network says it's parked, right? And that's based on millions and millions of examples, right? And so you can get really, really good results if you have enough data. So what does that mean? So if neural networks are doing most of the programming, what are the humans doing, right? Traditionally, the humans were kind of writing all the code and, building algorithms and tweaking stuff. Really, what's left to do in the new AI world is around the data side, right? Annotating the data infrastructure, right? Cleaning the data, right? That's really the main task. And if you think about it, this is what radiologists should be focusing on, right? The engineers really can't contribute as much on this side of things. So I think that's really exciting for us as radiologists, right? As medical people, because it means that the radiologist is the key component for building these superpowers. Obviously, we have to have the data. We obviously have to have people who know about the algorithm, but really the key differentiator is the radiologist. I'm just going to show you a brief example of this in real life, right? So this is an article that I published with my friend, I think it was last year, it's called the Hello World for Deep Learning and Medical Imaging. It's like the world's easiest machine learning algorithm, deep learning algorithm for medical imaging. And essentially, the goal is to detect whether an X-ray is a chest X-ray or abdominal X-ray, right? So it's vaguely useful, right? You guys probably have like X-rays that are mislabeled as chest when they're really abdomen or vice versa. And so, it's not really a huge deal, but maybe it should be sent to the chest radiologists, right? Instead of the abdominal radiologist. So it's vaguely useful. So this is exactly like dogs versus cats, right? So here's the code, right? So this is the hands-on portion of the webinar. Paula, we're doing that, right? People can take out their notebooks. I'm just kidding. So if you wanted to type in this code, by the way, this code is freely available online. The part in red shows you, the first parts just kind of load in the libraries that you need, right? Here, we define some hyperparameters. And then in this cell that I've circled in red, that's really the code to do, the training part. And that's how you kind of build the algorithm and create your weights, et cetera. So first of all, it's not a lot of code, right? If you kind of use this particular library. And secondly, I want you to notice that the only difference between the cats versus dog and the chest versus abdomen is the directory of the data, right? So I switched over to the directory with the chest x-rays and abdominal x-rays from the dogs versus cat directory. Every other line of code is exactly the same, right? And it works really well, right? So this is kind of an overly simplistic example because in building kind of more sophisticated radiology algorithms, it's not exactly going to be like that. But I'm showing you this to illustrate the point that really the only difference, right, and the only thing that matters is the annotated data. Great. So kind of having explained that, I'm going to talk about some of the larger scale projects that we've been working on with the societies in America. So I'll talk about the RSNA and then the SIM projects. And they were both based on the NIH data set that probably most of the audience knows about, the 112,000 chest x-rays that Ron Summers released, I think it was about a year ago, maybe a little over a year ago. And it came labeled with 14 different findings, except that the labels were really not, they were weak labels, so they didn't specify the exact area of abnormality on the image. And so what we try to do with SIM and RSNA is to create a better annotated data set. So in hopes that we could build a better algorithm. And so for the SIM portion of the crowdsourcing project, we took 15,000 x-rays from this data set. And we took all the ones that were labeled pneumothorax. And then we took 10,000 other x-rays that half of which were normal and half of which did not have pneumothorax, but were not normal. And then we invited a group of radiologists to help us annotate. Just to give you an idea, this is what it looked like when we annotated. This is a particular case with biapical pneumothoraces. And you can see the variation, right? And how people draw the annotations. We also annotated the chest tubes because a lot of times the pneumothorax cases will often have chest tubes. So I think when you're building an algorithm, you don't want to confuse, a chest tube with the pneumothorax. And so we finished that, I think it was late summer, and now we just met with the SIM board and we're ready to run a machine learning challenge. So hopefully some of you guys will be able to participate. And it's not officially announced, so I don't want to, talk too much about it, but it's most likely going to happen. We're going to kick it off during the annual meeting in June. So if you guys can go to the SIM meeting, that might be fun. And there's going to be a prize money for the top algorithms. So I'm excited about that. For RSNA, we annotated a data set in conjunction with the Society of Thoracic Radiology, so the chest experts. And this data set was bigger. We took 30,000 x-rays from that data set with 15,000 cases that were originally labeled as pneumonia. And we annotated the data set. I think there were quite a few radiologists, probably 20 to 30 radiologists total, who participated in some way. And we just published this in the new Radiology AI journal. So the inaugural issue of this journal just launched. It's online only, so you can look it up online. Just type in Radiology AI and you'll see it. And what's interesting is that we published the annotations as a data resource, which is one of the categories they have for the journal. So you can see the reference down below, but you guys can have a look. So these are freely available online to download. So hopefully, lots of you guys will have a look, download it, and use the annotations. Here's what it looked like. This time we drew bounding boxes around the areas of opacity. And this gives you an idea of how much variability there can be in terms of where radiologists think that there's pneumonia. And we also ran a machine learning challenge on Kaggle. And maybe some of the audience participated. This was last kind of fall. I think it was like maybe August to November, somewhere in that time frame. And that was really exciting because, RSNA had held challenges before, but, because Kaggle is such a popular platform for machine learning challenges, in this particular challenge, we got a lot more participants. So we had a total of 1,400 teams and 2,000 people. And for me, I've participated in Kaggle challenges before, but this is the first time I was hosting a Kaggle challenge. For me, it's particularly interesting. And I can show you some stats. So the top 5 participating countries, US and China, which is not a big surprise. And then India, Russia, Japan, 85 countries total. There's some of the European countries were in the top 20, but you can see that lots of activity from US and China. But what really struck me was that, so this stat is around 1,400 teams, 2,000 people, 85 countries, is that by, creating this annotated data set, right, and hosting a challenge, we were able to, and if you take kind of a rough approximation, let's say every one of the 2,000 people spent about 100 hours participating, right? Some spent obviously less and some spent a lot more. That generated, 100 work years on pneumonia AI. So we're really able to kind of focus a lot of effort around building an algorithm for pneumonia. And so for me, that's a very powerful thing for societies to be able to, create data sets, and that on a specific disease, maybe that's important to them, and have, the scientific community around the world focus on that specific disease. So we were really excited by that result. So maybe there's an opportunity for, Europe and the US to work together, either this year or potentially in the future. All right, great. And finally, I think, one of the ways that we're going to be seeing these, AI algorithms in practice and interacting with them, it may be through protocoling, right? I did Eric's podcast recently, and we talked about how, maybe we'll be doing, in addition to kind of our standard protocoling, we'll be doing some AI protocoling, right? And so I just created a couple slides on this. And so this is maybe a standard, pancreatic protocol for, pancreatic carcinoma. But in the future, we're going to be adding, which, in addition to how you acquire a particular CT scan, which algorithms are you going to use to evaluate the images, right? So maybe you have, 5 different algorithms for pancreatic carcinoma, and you pick, number 1, number 2, number 5, right? And then for the pancreatitis part, you would pick, a few other algorithms, depending on, you would probably be familiar with those algorithms and how they work, and have an idea of which ones would work best for the kind of patient that you're about to protocol. So it's, I think, maybe one way that we can think about interacting with AI in the future. Great. So that's basically it. So in summary, AI, machine learning, and deep learning, I think most people are basically talking about roughly the same thing, unless you're a computer science person, in which case you would not really like my definition of that. But for most people, when they talk about AI, they're talking about deep learning. AI is really about prediction. So make your problem a prediction problem to use AI. Hopefully you guys remember the 3 ingredients for AI, right? The GPU, the algorithm, and the hardest part is the annotated data. And doctors control this. And as a result, doctors can and should be building AI. And finally, I think AI protocoling will be performed by radiologists. Great. So next week, I'll be at the ECR. Hope to meet some of you or all of you there in Vienna. Thank you.
All right. Thank you, George. This was a really great presentation. Thank you very much. It was really clear. I think very interesting for most of the attendees, because you explained it really well stepwise, and also the way we are going and the way radiologists should engage. I really like this, and I think we should make the radiology community more aware of this and of the importance of our role in AI. Well, now we can start with questions. So yes, I don't know if there are any questions in the Q&A box. Maybe the listeners, yes, there's a few questions coming in now. If it doesn't work with the Q&A box, people can always use the chat as well. But I will leave the questions to Daniel.
Yeah, okay. Thank you, Eric. So, hi, my name's Daniel. So there's a question from Felix Worrigen, I assume is it pronounced? So can AI integrate the contextual information? So I assume this relates to if there's a specific part in the image that is somehow related to another part, does this context information get integrated, or even other information like clinical data? What's your view on that?
So, most of the algorithms today are not very sophisticated when integrating diverse data sets. Yeah, so EHR data with imaging data. I'm not a super expert in this area, but I think it's a matter of time, right? I mean, I think part of the challenge really, and I've talked about this before, is that in general, data is just really hard to get, right? So it's hard enough to get the kind of pixel data. If you're lucky, you might get some reports that match up with the pixel data. And historically, a lot of this data has been stored kind of separately from the EHR. So kind of getting, and there are places and, databases that can match this up, but I just think that part of the challenge right now is to kind of even get all these data sets together in a way that's coherent so that you can try to train on them.
Right.
So
maybe before and somebody else asks a question, there is a question from my part which I've been thinking about in the last days. So how do you see the market situation actually for AI? Because I mean, it's sure that AI can really unleash kind of superpowers, but I mean, I would expect that there are lots of startups now, but they will have trouble getting into the market because you compete with the doctors, let's say, in a situation where resources are limited, so money is not endlessly available.
Right.
What's your thoughts on that?
Yeah, I mean, I think that the market is going to evolve quite a bit over time. I don't think I've figured out the exact business model for the different AI companies out there. But I think that these payment models take time to work out, right? And I think they did historically for lots of other kinds of software as well.
Right.
And there are things like marketplaces that people are trying out. I think the PACS vendors are trying to figure out how to integrate these algorithms. And I suspect that the people that will that can kind of stay in the game longer will have a better chance of success. In other words, I think that it will take a couple more years to figure out.
Right.
Partly because most of the radiologists today who are using AI, and there are not that many, it's still more of a no, I don't want to say distraction, but it ends up taking more time.
Right.
At least from the reports that I've seen, than it has helped them, right?
Yeah, exactly.
And so I think if we eventually create kind of the right kinds of standards, right, which I'm sure your society is working on, and as well as RSNA and SIM and others, this will be a lot easier. So right now it's basically a playground, and people are kind of
right.
I also have a question regarding this, George.
Mm-hmm.
So yes, it's related to your proposal to work with a protocol type of AI model.
Mm-hmm.
So at this moment, as you said, not too many radiologists are using this already. most of the AI applications are being used in the academic centers, I think. But suppose you, well, at this moment, the startups are offering their products through some kind of a marketplace, a platform that radiologists have access to so that they can, let's say, activate it through the PAC system they have. But the question is, if you want to work with a protocol type of model, then you would have to, let's say, incorporate several algorithms in your system standard. They should be available. And then the question is, if you should have different products from different vendors, or should you only be able to use the products that you developed yourself? So how do you see this?
I mean, my view of it is that, we should, there are going to be standards, right? And I have a particular view on what might or might not happen, but yeah, we should definitely be able to, pull and use lots of different algorithms. It should be a combination of, lots of companies that have algorithms, but also, researchers who, right? You don't even have to be a researcher, right? I mean, you might want a version of an algorithm that, you've trained on your patient population. And so I think, I think there needs to be some kind of way to easily kind of pull down different algorithms from different vendors. And I think part of it is PACS integration, but I'm not convinced that that's the main part. In other words, the part where you get to select the algorithm, that may or may not kind of have to be in PACS, right? That obviously the output and being able to see the result has to kind of reside in PACS. But I think there are lots of other components on the back end in terms of where the algorithms live and how do you figure out which algorithms to use, that really doesn't have to have the same user interface as PACS. I think that's something that people should be working on.
Mm-hmm.
There's a couple more questions from the audience. So one is probably following up on that question with the contextual information. So again, Felix is asking if the AI is able to take information just such as gender, age, weight, and everything like blood values and patient history into account. But I think that was kind of the question you already gave, that this is probably something that we will see evolve over the next years. Or
so I think definitely can. So the way that I've seen it being used today is that when you train the algorithm, that it's a pediatric patient, or that it's a man or a woman, right? And so when you're running it, when you're inferencing, when you're trying to predict, you also incorporate that kind of information in the output, right?
Okay, but this is something like you would only choose the algorithm for a pediatric case, knowing that it is an algorithm for that case, but you wouldn't really think of it like an algorithm that then queries, I don't know, something for the age and then use this as input, right?
It could be either dedicated pediatric algorithms, right? But it also could be an algorithm that has seen enough pediatric cases to know that this is
okay.
a case. It could be both.
And then a question.
Aside from kind of, maybe age and gender, I haven't really seen too many other specific.
Okay. So this is probably something we will see in the coming years. But another question there, and this is a question that I hear very often, and we would probably like to know your view on that, is like, what's actually your vision for the interaction between the radiologist and the AI, and who is responsible if the diagnosis is made wrong because of the output of the algorithm? What's your views on that? So like in terms of ethics and workflow integration.
Right. So I think it's a very sophisticated problem. Sorry, complicated, I guess is maybe the right word. So there's the problem of if you have an AI output and whether or not you decide to do anything about it, right? So maybe you kind of ignore it. So what happens then, right? There's obviously a problem if you use the AI algorithm and it's not correct. So, you know, I think that, I personally think that the way that we should think about AI is similar to, you know, working with trainees, you know, residents and fellows, right? So they're going to give you their impression on a particular case, and then maybe even generate a preliminary report for you. And then you have to really decide whether or not you agree with that or not. I think from my point of view, that makes the most sense. That's something that we're used to doing already. We're used to trying to incorporate different, you know, information from different sources, but also from different people. You know, maybe there's a consultant, there's a specialist that comes in that gives you more information, and then you try to incorporate it somehow.
But this is probably like a short-term view, I would say, because I mean, then there's more work, let's say. But would you have a long-term vision? Let's say, do you even think that the algorithms will be able to perform equally to a fellow, let's say, and that you, or would you even say that it performs equally to the consultant? What's your vision? Do you actually think that there's a replacement that will happen, or will it always be a collaboration?
Well, I mean, I think eventually, right, the algorithms will be, they may not be better, but people are going to want to use them, right? So in other words, like, maybe I can measure, you know, all the 15 metastatic lesions in the liver manually better than the computer, right? But I don't have enough time for that, right? So at some point, you know, these algorithms will be good enough so that you will more or less accept what they say. I mean, you should double check them, right? But if it's, you know, 0.1 off, are you going to, you know, go to that level of correction, right? So I think they'll definitely be useful, and in those cases will be more powerful, if you will, right? So if, you know, if that's the level of detail that we want to be able to provide, I think we're going to have to rely on algorithms. In terms of how they interact with radiologists, you know, I think it's an open question. I think that, you know, what we haven't done very well in healthcare, in my opinion, is that, you know, the rest of the world, they're using iPhone, and, you know, Android's gotten a lot better, and, you know, the websites are all pretty user friendly, right? Good user experience. I don't think that we've invested a lot of time and money into building nice user interfaces for a radiologist.
Right.
I think you know, the newer systems are definitely getting better.
Right.
But I think that we need to invest in that space.
Right.
So that we can kind of figure out what the best user interaction is. I think a lot of times, you know, most of the user interaction is not going to, most of the work is really going to be behind the scenes. And we're probably going to be shown some kind of summary, which we can kind of say accept or not. I don't know if the audience uses Gmail a lot, right?
Yeah.
So you know, Gmail has the new kind of, I guess it's AI, right? It kind of predicts what you want to type.
Yeah, right.
It's really scary, right?
So
I think the danger in AI is not that it's going to be better than radiologists. The danger is that it's going to be so much easier, right, to just hit the tab button.
Right, exactly.
Accept whatever Gmail, you know.
Exactly.
You're going to just like want to use that, right? Because,
yeah. Hello, George. No, sorry.
Sorry, Nadia. There's two more questions from the audience that I just, for the sake of time, I want to ask them. So N was asking, what do you think would be the best way for radiologists to prepare themselves for these upcoming challenges? Let's say in a world where AI is present.
So you know, as a person who works with a lot of students, right? There's nothing like kind of, learning a new domain, like working on a project, right? And so even if you don't have any technical experience, but you somehow participate in, some kind of academic project, either at your local institution or maybe with a society, or even with a company, right? If you help them, you consult with them somehow.
Right.
I think that's kind of the way to get involved, because
so more hands-on kind of approach, probably.
Yeah, until you work on a specific project, right? It's hard to imagine kind of all the different things that are important and that you need to think about.
Right.
Yeah. And
So oh, sorry, please go ahead.
So one more word on that. I think the societies are starting to work on a lot of more relevant educational content. And there's a lot of good quality education content there. But it's not really focused on radiology.
Right.
And just a plug for RSNA. So a few of us, including myself and Brad Erickson, are going to work on a deep learning curriculum for the RSNA, really tailored toward radiologists, and I think something similar. And I'm sure you guys are also thinking about it.
Yeah, actually, we were thinking about that. So just one more question from Felix again. So what would you think is the biggest challenge and the biggest threat and probably the biggest opportunity in AI in radiology, like for the upcoming 5 to 10 years, like middle term, I think?
So I think, we talked about briefly finding a financial model to make it feasible, right? I think that's definitely kind of a big challenge for us. I think I like to think the developing world is the biggest opportunity that we have. I think, there are plenty of places that would benefit from, academics or even non-academics from participating in AI projects that try to benefit, the developing world using AI. And then, obviously learning from that experience and trying to use that as a way to gain momentum for their own countries, right? Because it's often too hard to change, existing workflows to accommodate something that's seen as experimental or there's no evidence behind it. But if we can rally around certain use cases and actually have benefit for certain patient populations, it's a lot easier for us to lobby for being paid for XYZ once we have some more information. So I would like to see a lot of us working on projects that are important for developing world.
All right, George, I have one more question. I'm often thinking about what will be the most probable scenario. I'm always thinking in two kinds of scenarios. That's the push versus the pull scenario. The push being the one where radiologists will start using it and will get trust in AI, and they will start implementing it for many examinations. And the pull scenario is the one where, let's say, clinicians and patients and maybe insurance companies will ask us or demand us to use it, because otherwise they will not, or radiologists can be, let's say, regarded as bringing insufficient value. So what do you think is the most likely scenario?
So I think that in probably most of Europe and in America, it's going to be driven by radiologists. I don't think that there's a way to kind of force a radiologist to use a particular algorithm. At least historically, that's not the way that we practice medicine. But again, I go back to developing countries, and I've seen in not always developing countries. I mean, there are plenty of developed countries that have shortages of doctors. If we can't cover those exams in a timely fashion, I think there is a big potential that the insurers or the government will say, look, if you guys can't read these in time, let's use an algorithm, right? And so, so I think at least for America, I don't see that coming from the government. I see it coming from the doctors, but it's probably different given the scenarios.
Yes, but maybe radiologists should keep that in mind, and it could be an additional trigger for them to start using it.
Yeah, exactly. And I will say one more point is that sometimes these deployments, and I'm not saying all of them, but I've heard that, it's like automatic, right? Like you always send the data to the AI, right? I think that's the wrong approach to start, right? Because if you're sending all your CT, lung screenings to AI, you kind of almost force the radiologist to at least look at kind of the different areas that the algorithm picked up. So I think it should be used on an ad hoc basis initially. Like, I'm not really sure about this nodule. Let me see what the algorithm says. I think that should be the initial model.
I have one more question.
Yes, please go ahead.
Yes, you showed us some example of thoracic imaging, and indeed, when we review the abstracts and everything, we see a lot of examples of it. So, how long you think it will take to get to another subspecialties? Like for now, we have less things on artificial intelligence in neuroradiology, on head and neck imaging. So, do you think there is something more appropriate in thoracic imaging, and it will take more time to go to another subspecialties?
So my impression is that these initial algorithms are driven by two things, right? One is the availability of public data, and number two, kind of the quote unquote difficulty of the specific problem, right? And so there's a lot of chest CT data, right, out there, and so and it's also from a algorithm perspective, I guess it's not easy, but it's probably relatively easy compared with some of the other problems that we're trying to solve. So I think you're gonna your answer basically is dependent on when we can release more public data, right? And also things like holding challenges, right? So if there's a great data set and we crowdsource these annotations and we hold a challenge on some specific disease, then you get the whole world focused on that, right? And I think there's a higher chance of building algorithms, and some people are going to commercialize those, right? So I think that's what I would.
Okay.
So we need to work on it.
Yeah, we need to get organize around things that are important to us.
Yes, and also define the right clinical use cases. What are the first algorithms we should work at? So.
Exactly.
Okay, so I think we can finalize the webinar here. It has been great. Thanks again, George, for doing this. And we also had a great discussion. So yes, I'm very glad that we had this webinar. So let's conclude here. And as you see, the attendees can still contact George. His mail address is on the screen. So thanks again and have a good evening.
Great, thank you.
Thanks.
Thank you.
Bye.
Bye-bye.